Today I'm going to be giving my talk on the zircon geochemistry of volcanic rocks in Hishikari, Japan, to do with the low-sulphidation gold deposit. So this is from my master's here at Imperial and at Natural History Museum last term. So yeah, let's get into it. So starting off with gold, it's very critical for electronics. So in particular, talking about solar panels, and it's also good for decarbonisation and just going further with trying to keep the world a better place, less carbon. Start off with epithermal. It's the main kind of ways that we're getting gold at the moment is placer and orogenic gold deposits. But epithermal itself accounts for about 13% of the modern gold production. And it's good because it's got the highest grades, actually, 2 to 70 grams per ton. And Hishikari itself, the location that I'm looking at, locally exceeds 1,000 grams per ton. And this is good because it keeps the higher grades are better environmentally because it takes less effort to take the gold out of the ore. So epithermal deposits themselves, there's two kinds. There's the high sulphidation and the low sulphidation. High sulphidation itself, very spatially linked with magmatic intrusions. It has hot acidic fluids, and it's very well known that the fluid source and the metal source is coming directly from the magma. Whereas low sulphidation, which is what I'll be talking about today, it's known to be kind of at the periphery of volcanism, but not always. It's a lot cooler with neutral fluids, and it's dominantly meteoric. So it's really hard to find if there's a magmatic kind of role in this fluid, because any signature is all overprinted by the meteoric fluid. And it's not particularly too close, so there's not really a lot of volcanism as well that's quite contemporary with it. So moving on, Japan itself, it's on East Asia, as I'm sure you know. It's a very thin crust, less than 35 kilometers thick. It's barren, it doesn't really have any porphyry copper deposits. It's been subduction has been dominant since the Mesozoic. And most of Japan itself is really just dominated by these big accretionary wedges. There's two main kinds, in fact, in southern Kyushu. There's the Jurassic, and then there's the more Paleogene to Eocene. And as you can see, the red triangles here, this is the volcanic front at the moment. So we're currently in a period of extension, but it's well known that Japan itself has been through multiple periods of extension and compression in the last few million years. So moving on to Hishikari, we've got the two volcanostratigraphic groups. There's the northern Kurosonsong group, and this is the kind of cooler colors that I'm going with, so like blue and purple. The darker the color, the older the unit. And then we also have the southern Shishimano group, and this is what the veins are hosted in. So you can see the gold star is where the portal to the mine is. And on the stratigraphic column, you can also see below it is the Shimanto supergroup, and this is the basement, which is the accretionary wedge. And above it is some pyroclastics from caldera formation recently. And then we also have on the stratigraphic column, we have older andesites going up to younger rhyodacite. You can also see that the mineralization is hosted within the volcanics. So it's in the lower Shishimano andesites, about here. It's also in the Shimanto supergroup, as I'll show in the next slide. They're about northeast, southwest. And it's also about the same age as the younger parts of the Shishimano andesite. So with a little bit of a cross-section, you can kind of see these veins are hosted in both the Shimanto supergroup and the lower andesite of the Shishimano group. So we know that it's temporally and spatially related. What other evidence is there that maybe the magma is having a role? And so there was a paper on lead isotopes. These lead isotopes should only really change from mixing fluids. And what you can see is the two black circles from they're the isotopic signatures of the lower crust and the basement. So meteoric fluid going through them should pick up those signatures, so you can create a tie line between them. And any veins that are hosted in only the basement rock should just have that signature if they weren't related to volcanism. But as you can see, the purple area, which is the veins that are hosting the basement rock, actually starts to tend towards the magmatic signature, even though it's not really spatially related in the column. So there are also fluid inclusion studies which show that there might be some involvement with the magma, but protrusions are not exposed. So how do we actually evaluate the magmatic evolution? So we're going to talk about zircons. They're common in silicic igneous rocks. They're physically and chemically resistant, and they also partition REs, which are the rare earth elements, the lanthanides, in a predictable pattern, allowing us to record water content, oxidation state, and composition of the magma. And they also, very importantly, incorporate uranium and exclude lead, which means that when you're looking at uranium-lead geochronology, the only lead that should be in the zircons is radiogenic, which is very good. You start with 0 lead, essentially. It's also very well categorized in porphyry copper deposits, where metal fertility is researched in depth. What is fertility? Well, it's magma's capacity to be able to retain chalcophiles to a shallow depth before it exalts them and has the capacity to create an economic deposit. Usually, it's used in porphyry copper deposits, but we'll talk about it in relation to low-sulphidation today. So oxygen fugacity is the main control, and it's basically just iron 3+ over iron 2+ ratio. And the main thing that we really need to care about is that sulfur is more soluble as it's more oxidized form S6+ rather than S2-. And as you can see by this graph over here, it kind of has a little range that it goes up to that by, and that's between 1.25 and 2.35 log units above the phyllite magnetite quartz buffer, which is just a buffer of chemicals that will stay at the same oxidation state no matter the temperature and composition apart from that. And then, so essentially the main thing is an elevated oxygen fugacity allows sulfides to stay in the magma for longer, and it keeps chalcophiles dissolved. It's mostly affected by higher water content, more evolution, and assimilation of oxidized country rock. So the aim of the study was, using all of that evidence, can we have a look at the zircon geochemistry and other low sulphidation system and see if the volcanism has actually affected this mineralization, and then compare that to whole rock data in previous ages, interpret the evolution of the magmatic reservoir, and then contrast that to porphyry copper deposits. So the whole rock data, this is actually whole rock data from Japan, just to compare it. So you can see it goes from basalts to rhyolites, kind of in the calcalcline suite, and just having a look at these quickly. This is silica on the x-axis, and then the major oxides, which are shown in the top left corner on the y-axis of each. So adding my data, you can see that we have these two andesites. So the blues are the Kurosonson again, and the oranges are the Shishimano. They go from andesite to rhyodacite, as was expected. And then, as you can see in these Harker diagrams, everything's decreasing apart from silica, potassium, and sodium, which is good. It's just showing that we're in the calcalcline suite. It's what you'd expect for an arc system. And then these were my zircon ages. So just moving on to the zircons now. Each of these vertical bars is just showing the kind of error range for each of the zircons, which is bad on their own. But when you collect like 80 or so from each sample, you can put them together and create a weighted mean age. And what we got from that was we have kind of these three main clusters of groups, even though we have two volcanostratigraphic units. And they're kind of clustering around, well, this one's 1.5, 1.1, and then 0.7 million years, which is good. We've got about 0.4 million years between them. And this one's the Kurosonson andesite, this one's the Shishimano andesite, Kurosonson rhyodacite, and Shishimano rhyodacite. And it's weird that we've got them together, but I think it's probably just because the zircons are coming from this one combined reservoir before they erupt separately. And so from that, and then also from the geochemistry later, I decided to put them into these groups. So we've got the pre-mineralization, early mineralization, and late mineralization, named because then when we look at the Hishikari vein ages, we can actually see that the early mineralization group is about the same time as just before the mineralization, within about 10,000 years. When late mineralization is again within 10,000 years of the end of the mineralization, which is good. So if we have a look at the trace elements now, we're going to first look at the REs, where we have YB over GD, which is just heavy rare earths over over medium rare earths. And we do that because of amphibole. Amphibole here is this blue line, and you can see it has this like kind of curve up in the middle and then comes back down at the end. Essentially what this is saying is it likes to take in the middle rare earths and doesn't like the heavies. So when that comes out of the melt, it leaves heavies in and takes middles out. So YB over GD should increase. And what we have on these graphs is we can see that pre-mineralization to early, it increases, and then early to late, it stays the same. And that's just saying that there's fractional crystallization occurring. And then if we have a look at these, well, so this data is just the difference between the groups. So it's just saying what's happening but in those 0.4 million years between them. And then this data is core rim data, so we take an analysis from the core and the rim of the zircon, and we say the difference between them is what's happening during zircon growth. So we can also see that amphibole is happening during as well as between. And then if we have a look at titanium, so titanium is correlated to temperature. So as you decrease with titanium, you decrease temperature, which you can see, again, look at the same trend, that pre-mineralization is decreasing, and then late and early kind of stay the same. If we look at thorium uranium, it should stay the same because we have no thorium-loving phases in the melt. But what we seem to see is we see pre-mineralization going to early mineralization, staying the same. Early to late seems to go up, which is interesting, and we'll talk about that later. Also, for the core rim of the late mineralization, it seems to be going back in both thorium uranium and YB over GD for 30% of the groups. Again, talk about that in a minute. So some of the trace element proxies, I'm going to start off by talking about europium. Europium itself has two stable oxide states. The first one is 3+, which is the same with the rest of the rare earths, apart from cerium. And then the other one is 2+. So plagioclase loves 2+, europium, and it will take it in as much as possible. And whenever you see a rare earth element graph, you'll always see europium being much lower in zircons. But water suppresses plagioclase. So that increases its kind of anomaly when there's more water present. And what we can see here is pre-mineralization increases to early and late stays the same, which is good because it's showing that we're getting more water-rich magmas, which is good for mineralization. And then we have another graph, and this shows temperature on the bottom, and temperature is, again, the same as titanium. It's just adding some extra little factors to think about. It's just saying the same thing, it's decreasing. But then looking at the oxygen flagacity, which is what we were talking about earlier with the metal fertility, and I've shaded in gray the kind of transition zone. We see it does increase after pre-mineralization, but it doesn't really get up to the kinds that we want to see for porphyry copper deposits. It could be above or kind of in the boundary where the sulfides go to the sulfates and they stay in the melt. So they're probably fractionating out. But with the europium, we do see that it is slightly above. Well, this dashed line is showing about the porphyry copper deposit limit of when it starts to become like good wet melts. It's good for porphyry copper deposits. And we're seeing it on the boundary, so they are wet, but not that wet. Anyway, putting it all together, making a genetic model, we start off with the Curasons of andesite. It's kind of fractionating, it's erupting, it starts evolving with fractional crystallization, increasing YB over GD and decreasing temperature as it evolves. And you have the zircons crystallizing with the Shishimano andesite kind of erupting immediately. Zircons stop crystallizing, and the melt keeps evolving and becoming more silicic, and then it erupts the Curasons on rhyodacite from the same chamber. And then what we think has happened is because the pre to early is the same time period between the early to late, it should be that YB over GD should increase the same amount and titanium should decrease the same amount. But the problem is we're not seeing that. And what that might be is if that did happen, and then we had basaltic primitive injections into the chamber, that could place the signatures back on top. And then we're also seeing thorium uranium increasing. So if this basaltic injection had an increased thorium uranium, that could be suggesting that these are occurring in the chamber and changing these signatures to be more primitive. And that is good, and it then creates these Shishimano rhyodacite that have that kind of primitive signature, not the same as the Curasons and andesites, but still more primitive. And then, yeah, in conclusion, overall, we have the twofold kind of stratigraphic groups. They're different, but the zircons actually indicate the three major phases with one combined reservoir, with early dry hot magmas that evolved to be wetter. Then you have the basaltic injections that may have occurred at the same time as mineralization because they're happening between early and late. And they introduce a primitive signature as well as lots of water. And this water and the hotter magma might have cannibalized, it remelted these sulfides that were fractionating out and saturated water as well. And as the sulfides are coming in, it creates a sulfide-rich magma, and that goes into these volatile bubbles, which exsolve, and they add to the mineralization. So we're hoping that this means that it has actually added to the mineralization. Anyway, that's everything. Here's my references, and thank you for listening.